So I'm Frank Pfenning, and I'm going to give you a series of lectures on substructural logic and concurrent programming. This is the tentative plan here, and most of these words on the board won't mean anything to you yet, okay? But hopefully they will by the end of the series. So in the first lecture today, I will look at the fundamental nature of logic. And logic is not the study of truth like some people think, but logic is the study of inference. So we need to, if you want to understand logic, we need to understand the nature of inference. So that's what the first lecture will be about. And then in the second lecture, we'll talk about inference, in particular, kind of very weak logics. And we see a strong connection between inference and these very weak logics and automata and other kinds of machines like Turing machines. And then the third lecture will beef up the logic somewhat, and we'll see that there's a close connection between that logic and concurrent programming. In lecture 4, we'll actually just mostly do programming, hopefully. And the language we'll be using is concurrent C0, and one of the co-authors, Max, is actually here, so you can blame him for everything that goes wrong. We'll send on Piazza instructions for how to download it and install it. The language will make no sense to you right now if you download it. Even though there is like a formal syntax description, it won't help you very much. By the time you get here, you should know enough to be able to use it. And on lecture 5, I'll talk about some more recent stuff, sort of at the edge of our knowledge and very close to the common research that's going on right now that I'm working on people in my group. So today, I'm going to try to go through these. Now, I should say that a lot of the materials are online. They're lecture notes from a course that I gave last fall at Carnegie Mellon. And I'm going to try to take about 16 lecture works of material, okay, and pack it into roughly the first 4 lectures or so. Of course, that's the problem. So I'm actually going to take a very small subset of those lectures. But the stuff I will talk about is mostly in those lecture notes, so you can read those. And I will post pointers to them on Piazza. And there's also program homework assignments that go with the lecture notes. Many of them will make no sense because we won't have talked about what you need to know, but some of them will. And I will post also on Piazza which exercise I would recommend so you can test your understanding of what you go through in lecture. Okay, so let me do a few things about in generalities, and then let's go down to start down with specifics. So in terms of generalities, there's a very close connection between what we call constructive logics and programming languages. Okay, so I put some logics here that are of interest. So first one is Intuitionistic Logic, and there's a close connection to which kind of programming paradigm? Yeah? Functional programming. As Bob pointed out in his lecture, if you're trying to impose something called an isomorphism, if we're trying to say the two are the same thing, we will have to do violence to one side or the other. So we not actually want to look at these being like equivalent in some strong sense, but we'll notice a very strong and close correspondence between intuitionistic logic and functional programming. Actually, we will not, because I won't talk about that, okay? But other people have noticed that, okay? Now, the important point about this is that both of these things existed before the correspondence was noted. Okay, so people had done functional programming, combinators, lambda calculus, and so on. People had done natural deduction for intuitionistic logic, and the insight was, oh, there's an extremely close relationship here. Okay. Okay, now here is IS4, which is a modal logic. Okay, all the modal logic has very short abbreviations like K, S, T, S4, and so on. Okay. You don't need to know what it is. But this particular modal logic turns out to have a close connection to stage computation. And in particular, if you're trying to find a good explanation of what mechanism like quote and eval is about, okay, which you might know from some languages, you can quote an expression, and at some point you can decide to evaluate it. There is a logical counterpart to that, which is the IS4 modal logic. Okay. Now, IS5 is a different modal logic. And if you look at that one, then you find a correspondence here to distributed programming. So roughly, to explain that part, in a modal logic, you relativize the truth of a proposition to particular worlds. And you talk about not just something is true in an absolute sense, but it's true at a particular world. And then what that means computationally, you compute at different worlds, which are just different places where you compute. And then the modal logic gives you guidance of what kind of programming constructs you should have in order to do distributed computation, where the computation happens in different places. And finally, temporal logic, where you have time advancing in discrete steps, corresponds to something called partial evaluation. And this is this idea that instead of running your program wholesale, you run a piece of it, and what you get out is a residual program, which you can run in the next step. You get out not the final value, but a residual program, which you can run in the third step. And if you analyze it very closely, you'll see that it's very closely connected to temporal logic, because you run it at one step, you get an output. You run the result as a second step, you get an output, and so on. So there is this staging in this partial evaluation, which you can explain and better capture in temporal logic than has been done before. Okay? So we'll put a couple of more errors here. So one is a very weak logic called Singleton Logic. And this will correspond to a certain form of automata. And then here we'll put like linear logic or substructural logics. These are examples of substructural logics. And we'll see that this corresponds to concurrent programming, where I should clarify that by concurrent programming, we're talking about not shared memory concurrency, but message passing concurrency, where the various processes execute and they send messages to each other rather than communicating with shared memory. So this is message passing concurrency. Okay, so this gives you a guide. You see that there's always a very strong connection between the various kind of constructive logics and programming languages and notations. And this will be something we explore down here. Yep?
Is there a logic that's like shared memory?
It's a very good question. Here's your PhD thesis. Okay. Shared memory. Okay. PhD thesis. Okay. So I had one undergraduate who tried for a senior thesis project to do that. Okay. He failed because it's actually worth a whole PhD thesis. Okay. Well, that's a very good question. So what is imperative programming really? And you will see that a lot of stuff we do actually in the next few lectures has a very imperative flavor. So really, it all depends on how we define imperative programming, whether you get something that's fully adequate or connected to a logic of imperative programming in this particular style. So it depends on what you mean really by imperative programming. So we can have that discussion after we have gone through some of these things. It'd be good to come back to that question, so you have to remind me about that so we can have a discussion on that. Okay, so by the way, my lectures are very example driven. Okay, so there's details in the notes. You should always stop me if you don't understand something. I want to go very slowly in these lectures, make sure that you understand everything that I'm going through in some detail. Okay. So as a first example of deductive inference, I'm going to do graphs, okay? So path through a graph. All right, so I'll take an example graph. I'll give it 4 nodes, A, B, C, D, and I have some edges here which go between them. Maybe like this, okay? And the first thing I want to do is I want to give a logical representation of what the graph is, okay? So well, how do I give a logical representation? Well, I have to give logical propositions that describe the graph, and I'm going to use 2 forms of propositions, okay? So one proposition is node of x that says what x is a vertex lay or node. And I want to say edge x, which means there's an edge from x to y, or y to x, because I'm taking an undirected graph, so the direction doesn't matter. Okay? So for example, how would I describe this graph? Okay, I would start with saying, okay, well, node A is true. Node B, node C, node D. By the way, can you read that in the back, or do I need to write bigger? It's okay? Okay, so these are the nodes, and how do I describe the edges? Okay, so edge AB. Okay, edge BC. Edge, okay, I'm going to say AC and edge AD. Okay, so I get AB, AC, AD, and BC. Okay, and I'm lazy. So now I want to describe, yeah? Question? Okay.
How about HBA?
Yeah, so I could write HBA, but I want to express in general that the graphs I'm considering are symmetric. I mean, are undirected. So I want to describe by an inference rule, okay, that any graph I consider is going to be an undirected graph. Any proposed rules for that? Yeah? Yeah. So I'm not going to say implies, I'm going to use just inference rules. Okay, and I call that rule symmetry. If I have an edge from x to y, I also have one from y to x. Okay, does it make sense of describing undirected graphs? Okay. So that's a description of this particular one, but you can see how to do this in general, right? I write down the vertices, and I write down the edges, and I say it's undirected by saying this rule. Okay. So the next thing I want to describe, when is there a path from x to y in a graph? Okay. And I want to describe this by inference rules. You can infer by doing deduction when is there actually a path. Okay. So I'm not giving you necessarily a way to compute it. I just want to specify it by rules of inference. Okay. So I don't need any logical connectives, just rules of inference. So any ideas how I might start? Yeah? Transitivity? Okay. So transitivity would be if I have a path from x to y, and I have a path from y to z, then I get a path from x to z, and I would call that the transitivity rule. Okay, yeah?
Reflexivity, you always have a path from node to itself.
Right, and so how would I exactly write that?
Node A, infer path AA.
Okay, I want to say x because A is a specific node. Node x, path from x to x, and that would be reflexivity. Yeah? Contains.
So edge XY infer path.
Okay. So where am I missing something in the premise or in the conclusion?
No, I'm suggesting an additional rule.
Oh, an additional rule? Well, the edges, I don't think I want an edge from a node to itself. Is that what you were proposing?
No, I was saying there's an edge.
Oh, okay. If I have an edge from x to y, then I have a path from x to y, and that would be the edge rule. Okay? Yeah? Yeah.
Edge x and path x are different. The path of 0 steps always takes you to the same.
Yeah. I mean, it's a matter of definition. We can argue about that, and we can make a different definition, and you get a different set of rules, right? So I don't want to be particular here, but I think it's clear that these inference rules give you a way for reasoning about whether there's a path from x to y. Yeah?
Why does the reflection rule require node x while the others don't?
Okay, that's a very good question. So why don't I need to say that x and y are nodes here? Yeah?
You're not nodes.
Yeah, so this is an example of what we call a presupposition, okay? So whenever we say edge x, y, we mean to imply that x and y are nodes. So we don't write it as an explicit condition, okay? So we'll never actually say here there's an edge from one thing to another unless the thing that we're talking about are nodes, okay? Yep. Do we want a symmetry rule for path? Is there a path from x to y? Do we need that? So the question is, if there's a path from x to y, then we can conclude there's a path from y to x. Okay, first of all, is that a true rule of deduction? Is this actually okay? Should always be okay, right?
Well, it depends on the graph. If we have the symmetry rule in the graph, we get this for free. And if we don't, then we probably maybe not want it.
Right. So if we have the symmetry rule and we said we're only working with graphs which are undirected, then we should always, when we know the premise, we know the conclusion. So we don't really need that rule, okay? So this is an example. It's called an admissible rule of inference. Okay, so admissible means whenever we can derive the premise, we can also derive the conclusion. In some sense, we don't need that rule. You might still want to have it because maybe it makes our proofs shorter. Maybe it avoids doing a lot of extraneous inference. So there's nothing wrong with it, but it's not really required because this rule is what we call admissible. Okay? Other comments on these rules? Right, and so the question is, if you want to, you can prove maybe that it's an equivalence relation, then you don't need that rule because you prove it, or you put it in there and then you see immediately from the rules that it's an equivalence relation, okay? Those are all extremely good observations. Now I want to make one other observation. If I give you a graph there, like this, and I apply all the inference rules I can, what will happen? It will cycle. Okay, is there any place, time when I can stop?
When you can deduce anything else?
Right. So at a certain point with these set of rules, whether they have the symmetry rule or not doesn't matter, eventually I will have deduced everything that I can possibly deduce. Right? Because any new inference, I know what the paths are in this graph. In fact, there's a path from every node to every other node. Okay? And when I've deduced all of that, then I'm done. Any new inference I can take gives me a fact that I already know. Okay? And that is called saturation. So we can run these to saturation. Okay, and if you heard this keyword, this is the basis for this for a programming language called data log. Okay, you write down a set of rules which define your relations. You run them to saturation. When any new inference gives you facts you already know, at that point you stop. Therefore, at that point you know everything there is to know about your situation. Okay. Here's another question: what does a proof actually mean in this setting? The actual proof of something. For example, what is a proof that there's a path from Z to A, C to A? What does such a proof actually mean? Right, so the proof will indicate, okay, the actual path from C to A. Okay, so for example, there would be a simple proof that says, okay, start with the edge from A to C, apply symmetry to get an edge from C to A. Then you use this rule to get a path from C to A. Then you have an edge from A to D, you make that a path from A to D. And then you use transitivity to get a path from C to D. And you can read off from that proof exactly what that path is. Okay? How many paths are there from C to D? Yeah?
Wait, we haven't, one thing I'm sort of confused about is that it seems like we haven't defined what a path is. We just defined the notion of adjacency for substructural.
Okay, these rules are my definition of what a path is.
They tell you when there exists a path between two things.
Mm-hmm.
They don't tell us, like, in order to count the path objects, you
Okay. Okay, so I'll leave it to your imagination for now, and then I'll show you how to do that. But if you look at these, how many paths would there be from C to D? Yeah? Yeah, because if you say that a path is determined by the proof, a priori you would imagine there are infinitely many paths, right? So you can go around this loop many times. You can use reflexivity to stay at C, then you go to A, stay here, and eventually you get to D. There's infinitely many such ways to do that, which means there are infinitely many proofs that there's a path from C to A. Okay. When we saturate, we actually cut that off. We say, okay, now we have a proof for everything, and we don't care if there are alternative proofs. Right? As long as we have a proof, we don't care what it is. Okay, so now if I want to track what the paths are, okay, so now I'm going to use a different color. Okay, so let's do it in red. Okay, so in order to be able to talk about paths, I want to talk about edges. So I would actually name the edges here. So this would be the edge from A to B. This would be the edge from B to C. This would be the edge from A to C. This would be the edge from A to D. Okay? All right. And then here we would have something like, if there's an edge E here, then this edge E also serves as a path from X to Y. Okay? And then for the symmetry, we have an edge from X to Y, then the inverse E minus 1 is an edge from Y to X. Okay, so that's my notation for paths. And here, if I have a path P from X to Y and Q from X to Z, then I would say P followed by Q would be a path from X to Z. And here, it doesn't matter what the node is. Let's just call R, say, reflexivity on X is a path from X to X. Okay? Okay, so then let's get rid of this rule. Keep things simple. Okay, so now if I wanted to say there's a path from C to A, path from C to A, okay, what would be the path that I talked about earlier? How would we write that down? Okay, so we'll take A to C and then we invert it. So that would be the E edge from A to C inverse, followed by what? From A to D, the edge from A to D. Would anything else I'm missing here? I'm not using reflexivity here at all. I don't stay in place anywhere. So I could do that. But the path which goes from here to here, because it traverses this edge in this direction, and it goes from here to here, is just this one, right? The inverse of that edge followed by this edge. Okay, does that make sense? Okay. Yeah? From C to D, yeah. Oh, that was supposed to be a D, I'm sorry. Yeah, path from C to D, yeah. Yeah. Okay, and then I can ask the question, I think that you were asking in the back there, what is my notion of a path? I can have some equation that says under which circumstances I don't care about the difference between two different paths. So for example, I could say that if I have a path P followed by Q and then followed by R, that's the same, oh no, that's bad, S. That's the same as P followed by Q followed by S. And so on, right? So I can put some equations on those, and I don't really want to distinguish between various things. So the reason I'm playing this through is because all these themes will come up in the various logic that we're discussing. Okay? But important is a notion of a proof, and that we take the notion of a proof seriously in this kind of first class in this kind of development. Okay. Okay, does that make sense so far? Okay. So that's what I call structural inference, in the sense that we can only gain new knowledge. We never lose anything. Right? If we make an inference, we have two things which are true. We're allowed to apply an inference to get something new which is true, and it stays there. Okay. Now something really interesting happens when you actually get away from that simple idea and you allow things that were true to no longer be true. Okay. Because you can use inference to describe the change of a state of a system, for example. Okay. Okay, so this is example is the coin exchange. Okay, so I'm going to have three types of coins. Q, which is a quarter, which is 25 cents. We have D, which is a dime, which is 10 cents. And we have N, which is a nickel, which is 5 cents. Okay? And now I'm going to describe the relationship between those. And I'm going to say that if you have 2 dimes and a nickel, you can trade it in for a quarter. And the way I'm going to do that is actually by writing an inference rule. So if you have a dime and a nickel, then I can get a quarter. And I call this rule Q because I get a quarter out. Okay? But notice I have to read it very differently from I did my rules before. Because when I apply this rule, these things here that I know actually disappear as part of the rule, and I get this one instead. So applying a rule of inference here will actually consume the premises and get you the conclusion. Make sense? Okay, we need one more at least. How can I get a dime? Okay, how would I write that rule? Is if I have one nickel and I have another nickel, I get a dime, and I call this D. Okay, of course, from an ordinary structural point of view, these are very silly rules, right? Why would I write D twice here? Why would I write N twice here? Because if N is true, N is true. But the reason I write it twice, because you consume 2 copies of a D and 1 copy of an N to get 1 new Q as an output. Okay? So now I want to do something. What else can I do in my coin exchange? Yeah? Yeah, I can do the inverse. If I have a quarter, then I can get 2 dimes and a nickel. And if I have a dime, I can get 2 nickels. And let's call this the inverse rule for dime and inverse rule for nickel. Okay? All right, so now I want to have this little proof that if I have 3 dimes, I can get a quarter and a nickel. Okay? So I have 3 dimes. Okay? And I want to get a quarter and a nickel. How do I do that? Which rules do I apply? Yeah?
Inverse dime rule.
The inverse dime rule?
And the quarter. Yeah. The D inverse.
This one?
D inverse.
Okay. So the inverse, I get 2 nickels. And now?
You can apply D, D,
Okay, so I can dig these ones here, consume that one here, and get a quarter here. Okay? So, and this one is a Q rule. Well, these inferences are kind of weird just to read, right? But if you summarize that, what happens is the rule says this. If I have 3 dimes, then with a couple of inference rules, I can get a quarter, which is this one, and this nickel here over there will be left, right? So that would be to summarize that little proof here into the effect that it has on the state. Okay? So if I want to think about it as a state transformation, if I start with a state where I have a dime, and a dime, then I would get to, okay, by some kind of transition here, to a dime, a nickel, and a nickel, and I would say that's by D inverse. And then from there, I can get to a quarter and a nickel by Q. Okay, you see what I'm doing here? Yeah?
The Q rule makes sense. How do you guarantee that those 2 D's are indeed friends? Does that make sense?
Yeah, okay. So that's an excellent question. So when you apply a rule, you have to consume as many copies of the things as you have in the premise. You can't use a single D to satisfy this one and also satisfy that one. So that's critical to implement the rules, right? So that's for when we go from here to here, we take this one D and we replace it by 2 N's. That's fine. We go from here to here, we have to take this D. That's the first premise. We have to take this D, the second. And we have to take this N. This is the only. Yeah. With linear inference, there's multiple premises you get rid of. You have to consume all copies of that. Yeah. How do I know that? Okay, right, that's a very good question. How do we know that these rules are sufficient for all the exchanges that we want to do? So that's a meta theorem. You want to try to prove that. You could prove it, for example, by giving the worth of each of these in terms of some primitive, and then you would show that all these rules make sense and they're sufficient to prove everything you want to prove. But that's a separate consideration, right? And later on, when we come to different logics, we will spend a lot of time trying to figure out whether our rules are correct and sufficient, right? So here, it's kind of not a very interesting question. But okay, does this make sense? Okay. All right, so we can do coin exchange. Let's see, what do I want to do next? Okay. Next thing I want to do is go back to the first, or this board here. Okay, Shakespeare. Okay, so this is from Richard III, the Shakespeare play. I want to translate the sentence, "My kingdom 4 horse." Okay, so what happens there is King Richard is in this battle, and somebody kills the horse from under him. He falls off, and he's on the ground. And basically, he's in very dire straits, and he's willing to trade his kingdom for a horse so that he's back on top and can survive the battle. Okay, so I want to now capture this in linear inference. Okay, linear logic. So I can give you a vocabulary. Okay, so we have Richard, which is obvious, okay, King Richard. And then I want to say owns x, y. Okay, x owns y. I want to say that x is a horse and x is a kingdom, okay? And now I want to express the sentence, "My kingdom for a horse." How do I do that? Linear inference, of course, right? Any ideas? Okay, so we'll start with that. Owns Richard. Okay. K is a variable here. Okay. Yeah? Okay. X, Y, and horse Y. Okay. Are we done? Deduce. What do we want to? Owns Richard. What? Y. Okay, so that's a little bit of a questionable rule. It's not really fair trade, right?
Because we need to give back
Richard owns the kingdom, and afterwards Richard owns Y. Oh, okay, we need to say that K is a kingdom. Otherwise, it would definitely be unfair trade because it just gives you his pocket knife, right? Okay, so K is a kingdom, Richard owns K, X owns Y, horse of Y. Afterwards, Richard owns Y, which is good because Y is a horse. But the other things disappeared into thin air, right? What else do we need to do?
We need to give the kingdom to the other guy.
We need to give the kingdom to the other guy. Owns, what is it? K, right? Are we done now? Yeah?
We still need to say kingdom K horse Y.
Yeah, because, well, otherwise, X owns K, but K is no longer a kingdom, so what is he going to do with it, right? So we still need a kingdom K, and we still know that Y is a horse. Because otherwise, Richard wouldn't be able to ride it, right?
Do we want to somehow ensure that kingdom and horses are not duplicated? So Richard does not anymore own
Yeah, so Richard doesn't own K anymore because we have only one, he only owns this one kingdom, and when you apply that rule, that ownership disappears, right? Agreed? And presumably this guy, he might have multiple horses, it doesn't matter, as long as he can give one to Richard, okay? He might still own the other horses, that's perfectly okay. Okay? Are we happy with that? It's okay, it's kind of a fair translation. The only problem is that what this really means, from the point of view of Richard, maybe that's where you were getting at, is my kingdom's 4 horses. Because this is an inference rule, right? We can apply your rules as often as we want. So if Richard happens to have 2 kingdoms, right? The next guy comes along, hey, I have a horse too, give me your other kingdom, okay? So this rule of exchange that allows you to get in the kingdom by giving him a horse, you can only use once. Okay, so there is something which we can't really express very well, but this thing should be linear itself. The rule itself should be linear, right? Because if you apply it more than once, that just really wasn't intended. Does that make sense? Okay. The other thing is that in practice, we often want to have what we'll call mixed inference. There are some things which are ephemeral and they're being consumed by the inference, like ownership. When you have a change of state, ownership changes. But if you have a change of state, the kingdom will stay a kingdom and the horse will stay a horse. So that's really an intrinsic property. Okay. So what we sometimes do is we mark these things here, saying that, maybe I should do it in red. Okay. The kingdom is persistent, and the fact that something is a horse is persistent. So we need to check it, but then we don't need it here anymore because everything that's persistent is not consumed by the inference rule. And now we're in a situation where we can do the structural inference from the first board that's now hidden and the linear inference in the same system. Because structural inference just means whenever you do an inference, you keep what's there. And that's simply because everything is underlined, so everything is persistent, so it never changes. And then we have other things which are linear that once you consume them, they're no longer there, and they're replaced or wherever you put in the conclusion. Okay? So really, this is not just a linear example, but it's actually a mixed example where we have some linear things, they're ephemeral, that disappear and change, and other things that are persistent. Okay? All right, other questions on this? Yep. Yeah, okay, so that's a bit of a problem. Okay, so if I want to say, well, he said that, but let's assume you wanted to say not owns Richard H such that horse of H, and that would be presumably be underlined. Okay, so the problem is when you change your point of view and you say that inference changes the state, it's very difficult to test a property of a state. Because if you want to test something from a state, you have to perform inference. By performing inference, you change the state. Okay? So in ordinary linear logic, we cannot really express that. Okay. There was another question over here.
So kingdom is linear, horse is linear, and the rule itself is linear.
Yeah. Well, no. Owns is linear, and the rule is linear.
It's the opposite.
Yeah. And kingdom and horse are persistent. Yeah. Okay, so let's take one more step. Okay. So now I want to go from okay, so now I want to do grammatical inference. Okay, and this is actually something that was due to Lambeck in 1957 or something like, or 58. So it's a very old idea. And the idea is not only do I say when you use something it's consumed, but I also want to say that all my assumptions come in some intrinsic order. So my state is in some order. And the reason I want to do that is because I want to represent the process of parsing as a problem of inference. Okay? So how do I actually do that? Well, I have something called syntactic types. And we are just only going to use two syntactic types. Okay? S, which stands for sentence, and N, which stands for name. Or more general, something that could stand in for a name later on. Okay, two syntactic types. And then I have particular words. So for example, I will say Alice is a name, Bob is a name, and I may add some more words there as we go along. Okay? All right. So now I'm going to write a sentence out. Okay? Something like Alice works. Okay, and it's going to be in this order. Okay, so this is going to be an N. This is going to be something which I still have to figure out what it is. But I want the whole thing, okay, to become a sentence. So the whole thing down here should be a sentence S. And I want to get there by inference. Okay, so the way Lambeck does that, it says that works is something, which is a verb. If you have a name on the left, you can get a sentence. Okay, and so he says that the following way in a logical form: if I have a name on the left, this is a logical operator, then I get a sentence. Okay, that's the way he says that. And then you can make an inference. If I have something X on the left here and I have the same X over here, I can conclude S. So these two form a sentence because works is something takes a name on the left to give you a sentence. Okay? So here, works has type N under S. So that's how it's pronounced, N under S. Okay? All right, so that's yeah?
Writing N on the left-hand side of the horizontal graph doesn't really make it to the left of N/S.
It does, because the premises of the bar now are not just linear in the sense that they will be consumed, but they also have to be considered in order. Okay? So I can't change the order of the assumptions. They have to be exactly in order, and they have to be in my state exactly in this order for this inference to work. Okay? So I'm making a very strong restriction here, and it comes on top of the linearity restriction. My things will be consumed to make a sentence, but also they have to be in exactly the right order. So let's say, let's make a slightly more complicated sentence. Alice likes Bob. Okay, so Alice is an N. And I want this to be a valid sentence. Down here I want to conclude S. We know what Bob is. Bob is also an N. Okay, so what do I have to make likes for this to work out? So by the way, this is called an intransitive verb, and this is a transitive verb. So what would be the right syntactic type for likes? So N, so under S, and then? Okay, so we want N to the right, so there's a new thing that we need that says like that. Okay? Now I have to put parentheses here somehow. Which way do I want to put parentheses? This, like this? Let's put it like this. So that says I take a name to the left, then I get something which, if I take a name to the right, I get a sentence. Yeah, that's an excellent point, but let me finish the proof here. So the proof says, with this parentheses, I get then something which, if I give it a name to the right, and then this name, if I copy it down, I get S at the output here. Now, I could have parenthesized the other way. Okay, so I could have said, Alice likes Bob. And I could have said, this is an N. This is an N under S over n, and I have an n here. So then this inference is first, because I have an n to the right, I get n to the left gives me an s. Then this n together gives me an s over here. So I have a choice how to do that, right? And as a result, I get slightly different parse trees, right? This parse tree is kind of works on the left first, so it looks like this. And this parse tree works on the right first and looks like that. Okay, so depending on my choice on what I assign. Okay, so likes is something that takes n, and let's just say we're doing it like that. Looks to the left first and then to the right. Now, it'll be interesting to see by the end of the lecture today, we should be able to prove that this choice never matters. That something can be parsed with this choice here, exactly if it can be parsed with this choice. Because both of them mean look for an n to the left, look for an n to the right, and then you get a sentence. And the order in which you look doesn't matter, right? That's what we're trying to express. So logically, these two things should be equivalent. And we can do logical reasoning in a little bit. Does it make sense? Yeah?
Is that like a confluence property? Or?
No, it's an equivalence property. You can prove that the thing on the left implies the thing on the right, and vice versa. These are implications. Yeah. Okay, so we can do some more sentence types. Okay. Words type. Okay, let's say Bob works here. So we already know what Bob is. That's an n, and works is n under s. So what should here be? Yeah? S under s. Right? If there's a sentence to the left, then the whole thing makes a sentence, and then this gives us an s, and then this inference gives us an s, and we have parsed it. Okay? Okay. Right. Something more complicated. Alice never works. Okay, so I put here, what was it here, is S under S. Okay, Alice never works. So Alice is an N. Works is, what was it? N under S. Okay, so what is never? Right. It can't be, because it modifies works, okay? So it has to take to its right an n, n under S, and to its left it becomes an n under S. Okay? So the way you parse that is you first parse these two together. You have an n under S to the right of an n under S, and then you get this output here. And, sorry, I said over, and I think I made a mistake here, right? Like that. Okay. So these two should be identical, and I get n under S. And then I make this inference to get a sentence S. So never is n under S, yeah, over n under S. Okay, does all of that make sense? Okay, and you can go and you can try to do whole grammar that way. And I think we'll stop here because, you know, as a homework you can do some additional things, but it's pretty clear, I think, what you should need to do here. Now, what would it mean for the language to be ambiguous? So that means there's more than one way to parse it. What would that actually turn out to be here? You would have more than one proof, right? Because there's different ways to define the rules to get to the same conclusion that something is a sentence. Okay, and we need very little for that. We only need ordered inference, and we need two logical connectives, right? The over and the under connective, right? And then we can do this kind of thing. All right. So next thing we want to do is, what we want to express in the language is actually not that something can be parsed, but we want to express that it is a valid sentence. Okay, so what we want to express is this. If you have all the words up here, so word 1, which has type x1, word n, which has type xn. Starting from there, you can do a derivation, you can do a proof, and at the end, you get some proof that S is true. Okay? So I want to express this situation, that under these assumptions, I can actually derive S, so that these words form a valid sentence. So right now, I cannot express that. All I can do is I can express what are the valid grammatical inferences, but I can't say that I definitely want to get out a sentence. Okay? And so this is requires a new logical concept, namely that of a hypothetical judgment. And Bob already talked about this. So the way I'm going to say this is that W1, X1, Wn, Xn, under all those assumptions, I can prove S. Okay? And it's supposed to express exactly the same thing that this picture expresses. If I start with the state where these are all my words in order, okay, these are the things in order here, then I can prove from that that these form a sentence. Is that clear, what I'm trying to do here? Okay? And one of the reasons I'm interested in that is because I want to show that these two things here are equivalent. So I want to be able to prove this. If I have x under y over z, then I can prove from that x under y over z, and vice versa. So I can prove this in both directions. So I want to show that from the point of view of inferences, these two are actually equivalent. Okay, where you can use one, you can always use the other. And this logical inference requires us to talk about something like a notion of consequence. If I know these, I know that. But unlike Bob's lecture, I make very strong restriction. This context here does not satisfy exchange, does not satisfy weakening, it does not satisfy contraction. Okay? So I'm in a very, very weak logic because I'm making these restrictions. And this very weak logic allows me to have these connectives that refer to the position of things in the context. In Gödel's T, it wouldn't make any sense to say the variable to your left because the order of the variables doesn't matter. But here, it actually does matter where these assumptions are, so I have to be explicit about that. We okay? Okay. So once I have this kind of notion of a hypothetical judgment, then we have to figure out what are the rules for reasoning with this. And now there's something funny happening. Okay? So let me... Okay, so the funny thing that's happening is that my rules of deduction, which I have there, which I probably write out explicitly. Okay, so I have the following rule. If I have an x over y, and next to it a y, then I can conclude x. And here I've said if I have an x over y, and right to it a y, then I conclude y. When I start trying to reason about this judgment, okay, these rules have to change. Okay, and the way to change is the following way. So the under rule says like something like this. So I have some ordered context. I'm going to use omega for ordered context. L is just saying that this is to the left of what I'm interested in. And I have y, and next to it, y under x. And then I have some more stuff. And I'm trying to prove some z, which I don't care about. Then I can do that if, while the omega L is copied over, because that I don't do anything with that. And what I replace y and y under x by? X, right? Because if I reason here downwards, here somewhere I have x, y under x, and y. Then here I can make the inference and conclude x, which means now I have x available, which means that here to make it available, I have to actually turn this inference rule around and make it upside down. Okay. Does that rule make sense? And we call this the under left rule. Okay, because it works on the left of the turnstile. Yep.
And that's pretty similar to lambda abstraction.
Yes, so if you forget about all the orders and all this kind of thing, this is function application. So this is a function from y to x, this is a y to its left, and you get an x. Yeah? I'm not a linguistics researcher, but they really did it for a while. Okay, this is generally called categorical grammars and lambic calculus, and people prove, for example, that in the lambic calculus, under some assumptions, you can exactly represent context-free grammars. Okay, yeah?
More of a curiosity, but it seems like you replace these horizontal lines with less or equal.
Yeah?
And then the dot between it, you get this means the residuated lattice.
Yes, it is. That's what lambic, that's where Bob based the notation off. For, yeah.
But then you wouldn't need all these omega left if you had did it as an outward direction.
But we want to reason about a notion of entailment. And so then inference rules come in the end anyway, because not everything is just an equation. You want to say, with this, we can prove that. Yeah. Right. Okay. Any other questions? Okay. We also need a rule for over. What does that look like? Well, it's omega L, and we have x over y, and next to it to the right a y, and some more stuff here. Then we replace the stuff in the middle by x. Okay. Now this isn't quite enough yet. What am I missing here? With these rules, I will not be able to prove, for example, that Alice likes Bob is a sentence. Actually, in that case, it's just S, so I don't need to manipulate anything there, right? Because it just carries forward. But, yeah?
You need word introduction rules.
I need what?
You need word introduction rules.
No, because I seed the context with the things that are the sentence, that are supposed to make the sentence, and then I work my way up. So in order to parse something like this, I don't really need introduction because I'm just parsing. I'm just going down. But I do need one thing. Yes, one axiom, but what is it? Yeah, S is S, or in general, we need a rule that says if I have an X, I can conclude X. And this is called, well, the identity rule on X, right? The rules that Bob called indefeasible, right? If you have the assumption X, you always get the conclusion X. That's what the hypothetical judgment kind of means, that at the minimum you have that. If you know X, you can conclude X. Okay, does that make sense so far? And so when I build a proof, I work my way up on the left, and eventually I get a sentence, and then I close it off with the identity rule. Okay? Can everybody see that? In this very simple setting, that's what I'm doing. Okay. So now the problem is it doesn't help me prove that thing that x under y over z is the same as x under y over there. I can't prove that because I don't have any rules when I start. If I want to say x under y over z proves x under y over z. Okay? And I'm stuck. I can't work because none of the rules allow me to look at the right-hand side. And on the left-hand side, I don't have this. I don't have a z to the right of that, so I can't do anything, right? Okay, so how do I do that? Well, I have to figure out under which circumstances I can prove. I need to have some kind of a rule that says, when can I prove x, y under x? And here I need a rule that says, under which circumstances can I prove that x over y? So I need some kind of a rule that works on the right rather than on the left. Okay, how do I do that? Okay, so here is the idea. Y under x is something, if I put a y to the left, I get x. So now just write that down. It is something that, if I put y to the left, I get x. And that's the right rule. Okay? So y under x is something is something, if I put y to the left of it, I get x. So just write that down as an inference rule. Make sense? And then this over here, what would this rule be? If I have some arbitrary context omega, this would be the right rule for that. What would that look like? Nope. It's something if I put y to the right, then I prove x. It's hard to get these things straight. Okay, I've made the same mistake many times. Okay, but x over y, if you put it's something if you put y to the right, then you get an x. Right? Make sense? Everybody with me? Okay, so not in today's lecture, I don't think, but maybe the next lecture, we will be actually really concerned about with whether these rules really make sense. Intuitively, I tried to give an argument why it should be that way, but there has to be some kind of a formal check or some kind of a rigorous check that actually this makes sense. And this is actually not a trivial property at all. But let's just use it and see what we can do with it. Okay? I want to now prove that it doesn't matter where I write the parentheses there. So this thing here. Actually, I think I have enough room to put it right here. How do I start? Yeah? No, that's an overwrite, and this is a... Oh, no, that's the left rule, sorry. It's on the left of the turnstile. Thank you. Okay, so let's see if we can prove that. How do we start? Yeah, so you don't actually have a lot of choice. There's only one rule that can even apply, right? Because the left rule doesn't apply because you don't have a z sitting here. You can apply that rule, right? So then the next, we have x to the left of x under y over z. And on the right-hand side, we have y over z. Okay? So this was the under right rule. Okay, what's the next step? Can I apply left rule here? No, because the thing to the left of the slash would be a z. You still look for a z here. There isn't one. But we can apply the right rule. Okay, so that takes a z and puts it to the right here. So now I have x, and we have x under y over z, and a z to the right of that. And here we have y. And that's the over right rule. Okay, next. So now we have the z to the right of the z that we've been looking for this whole time. Now it's there. So now we can use the over left rule. And these two cancel, we get x and x under y. And we're still trying to prove y. Yes? Okay. Now what do we do? Well, now we can apply the under left rule. This x cancels with that. We get y proves y. And now we remember that we have this handy rule here of identity. And we can actually finish with the identity on y. Okay, does that make sense? Okay, and you can, the other direction, you can do the homework to prove that this thing also entails that. So these two things are equivalent. So wherever you use one, we can use the other instead. That's essentially what we're trying to say. Okay. All right, so let's see. So far we have in this logic only two connectives, the over and under, right? So let's see what other connectives we might have and what the rules for it might be. Okay. Can somebody think of another connective that might make sense here? So you're free to think of it in the downward direction, or you might think of it in the upward direction. Connecting two s's. Okay, so if you have two sentences next to each other, Alice works, and right next to that we say, okay, so let's do it like this. Alice works, and next to that, Bob likes Alice. Okay, so under these assumptions, I won't write anything. What should we be able to prove under these assumptions? So with these things, we should be able to prove S, right? Whoops, no, here. And with these things, we should be able to prove S. So really what we should be able to say, there's two sentences next to each other. I'm not sure if that's what you meant, but okay, that's the question. So we like to say S, and next to it, another S. So it's a form of conjunction. Okay, it says we have two things, but normally conjunction says this is true and that is true. But here we have to say this is true to the left of that. So we have to be very specific. They're next to each other. Does that make sense? As a connective? Okay, so what would be the rules for that? Okay, so that would be so we have omega L, we have X, this is pronounced X fuse Y, we have omega R, and we're trying to prove Z, and we're looking at what the left rule means, the fuse left rule. And you said having a projection, so you could just get X. Okay, this actually turns out to be not the correct thing for this connective, because to prove S fuse S on the right, both of them need to be there, okay? And you can't just drop part of what you're trying to do. So there is a connective which has this rule, but it's not this one. It's another form of conjunction, okay? So what would that rule actually look like? It can't look like exactly like this, but yeah, we don't drop Y, we put X and Y next to each other. So fuse just means these two things next to each other, which means that we have a fuse in the context, we'll just replace it by the components. Make sense? Okay, what's the right rule that corresponds to that? So we have to prove X fuse Y, because it's a right rule to fuse right. And presumably, according to this, we have to decompose it into proving the two pieces, X and Y, right? Okay, so what do we do with our string of words on the left, with our ordered context?
We know we are ordered, so we take the left part.
Yeah, so we know they're ordered, so we take the thing on the left and use that to prove X, and we take the thing on the right and we prove that to use Y, okay? So we can't mix things up, like we can't flip things around, put some things over here, some things over here, because then we wouldn't be able to parse things like in a meaningful way. We really need to make sure that this part stays together and that part stays together. And where you split depends on, well, whatever you happen to be able to prove. Right? If I put Bob like Alice first and Alice works second, then that would have to go that side and this would have to go to the other. Okay, so I have to split them like that, and here I just split it by moving it up. Okay, does that make sense? Okay. Let's see. Let's do one more example, and then next time we'll look at some properties of this kind of logic, but one last example I want to do. Oh, yeah?
I don't understand why your fuse left rule works. So it's like if you try to put X and Y next to each other, you're not going to be able to find them. It doesn't seem like just moving X and X is exactly.
Okay, so let's use it in a proof and let's see maybe how it'll come out. Okay, so let me do that example. So I want to show that, so in a functional language, you know this thing of currying, right? It says something like if you have A cross B, arrow C, that should somehow be equivalent to A to B arrow C, right? So instead of giving it a pair, you can give it the two pieces in sequence. Yes? Everybody familiar with this currying? So now I want to do something similar here, except with order. So it's tricky to figure out what that actually would mean, right? Okay, so this would be X, Y, Z. presumably like this. And there have to be some slashes in there. I'm not sure exactly which ones, right? And over here, I would have x. Now that I know is x fuse y. And then some slash here to give z. OK, so let's just say this is x fuse y with, let's say, OK, let's do it like this, under z. OK? What do I put under here so that these two things are equivalent and to say that we can prove this and we can prove that? Yeah? X under y under z. OK. Let's try to prove this thing entails that. OK? So x under y under z proves x fuse y under z. OK. How do I start? Well, I have to start with the right rule, correct? There's nothing I can do here because there's no x to the left. So here I get x fuse y, and next to x under y under z. And then over here, I try to prove z. So this would be the under right rule. So far, so good? Next thing is I break down the fuse, right, to get the components. So this is the fuse left rule, and I get x followed by y followed by x under y under z. And I have to prove z. OK, now what? No, I'm stuck, right? OK, so what is the right thing here? This was wrong, right? And I discovered it, but trying to do the proof. What should this be? Not x under y under z, but y under x under z. OK, so when I apply currying, I have to flip the two arguments, because then what happens is this is y under x under z. This is y under x under z. This is y under x under z. So now y is next to the y. Now I can apply the under left rule, and I get x followed by x under z, prove z. And now I can prove the under left rule again, and I get z prove z, which is the identity. OK, so now here was a question about the fuse. The reason that it works is because I just break it down to components, and then the pieces can interact with the rest of the context. I don't know if that answered your question exactly. Yeah. OK, so does this make sense for everyone? OK, good. So I'm going to leave you with a puzzle, which we're going to resolve next time. But basically, this says that if you use fuse anywhere, if we can prove both directions, you can just iterate the slash. You just have to flip the order of the x and the y, as you can see over there. Because this means x and y to the left of this, you get a z. And that means that the thing that's closest to the z is actually the y, and then the next thing is the x, and then you get z. Right? So first you have to observe the y, then the x. OK, so the puzzle is the following. Oh, I can't move that up. Put it over here. Let's do it here. So try to prove the other direction. OK, x fuse y under z proves that y under x under z. OK, so I put y to the left. I get y. X fuse y under z proves x under z. I put x over here. I have x, then I have y, then I have x fuse y under z, and over here I prove z. OK, so this would be the under right rule. So what happens now? At this point, I'm stuck, right? Because I can't apply the identity. These two things are different. I can't apply the under left rule because the thing over here is not x fuse y, it's x and y separately. And the left rule says if I have the exact same thing here and the exact same thing here, then I get this. And that's about it. That's all I could possibly try. Right? Okay, everybody see that we're stuck here? No rule applies. Okay? I think all the rules are on the board. So there's nothing we can do. So what actually happened was that we made a mistake in our rules. Okay? So we have to fix those. Okay, so that will happen at the beginning of the next lecture. We'll analyze this problem, we'll figure out how to fix the rules so that they actually work correctly. Okay? And then with the correct rules, we can actually talk about interesting rules of computation. Yeah?
Why doesn't the fuse left of that?
Because the fuse is hidden below this connective here. I have separately, but the fuse rule breaks it down into the components. It doesn't form a fuse. The fuse is, in these rules, whenever you go up, you break down the connectives rather than forming the connectives. So you really want to put these two together to x fuse y. That's what is screaming at you, right? Do that, please. I want this to be x fuse y. But you can't do that because you don't have a rule that actually constructs bigger propositions you're going up. Okay. Which left rule?
So we have x left to y, and we can use the dot left rule to construct x dot y and this right hand side, so that we can plug in the right hand side to get 3 and 5.
He's asking why you can't use this dot left, but you just said it's because it's under the slash.
Yeah, it's under the slash. It's not at the top level.
We can construct x dot y with the x, y, variable.
Okay, so I take the x and the y and construct x fuse y, okay? And then?
And now we have an x dot y, and we have x dot y slash e.
Yeah, but how do I actually, what do I do with this little proof here, right? That's a two-line proof, right? X proves x by identity, and y proves y by identity. So I have a little proof here, but how do I build this into the rest of the proof? That's the question, right? How do I connect it to the rest of my proof? Yeah?
You could add some sort of like dot left inverse, right?
Right. Yeah. So dot left inverse is very dangerous because when you're going up, you want to break down the connectives rather than building them up because otherwise you're going back and forth, and so that would be not a good rule.
It would solve this particular.
It would solve this particular problem, and you buy a whole host of other problems. So that's exactly the kind of solution I thought of at first, of course. But oh yeah, that's also really scary. Yeah. Yeah, distributivity is nasty because you have to look inside the propositions. You see what's below, and you want all your rules to just work on one single connective on one single side. If you have tried to look into these propositions, yeah, doesn't work.
So the better answer is we use something like what we did before, that like equivalence.
Well, the question is how do we use that equivalence? And we're trying to prove actually an equivalence here, right? Yeah. Yep. Okay. So it's something you can ponder over, or you can look up in the lecture notes, but think about it first. Okay, it's more fun that way. And then I'll give it away next time. Okay.